So it turns
But
out.
usually I don't think a lot of people use GitHub there. It's mostly
I know
GitLab
for
or something like that.
Yeah.
Because
So
GitHub
multiply it
becomes
together,
very
it's just doing
expensive.
something.
For
Yeah, but
private.
Shouldn't that broken?
We in our
Yeah,
office
I
we
know
had
how
a GitLab
Somebody's gonna
deployment.
get there either way.
So what is called
That's always also inside our
So it's like-
So there are probably more. There's probably less of this on GitHub than like. Yeah.
Yeah.
That's so thank you. Yeah,
So I
appreciate
think
that.
what's happening is it was doing.
Another point.
Homework 3? Done?
Then when I multiply it, the whole Yeah, done.
You get some help outside the evening hours?
I haven't asked it yet, but I can do it. No, I don't need it for now.
So yeah, we still debugging neural networks. I think we can't delay that for too long. As I said, I don't want to have strict deadlines, but we can't delay for too long because we're a little behind with the assignments. We are not behind with the lectures, but you realize I'm almost done with. This is the last lecture on generative and Gaussian stuff, and you guys didn't even start thinking about those things, right? So yeah. Plus there is a spring break that's coming in, right? So what we're gonna try to do is to have a lot of the help for homework 4 that's coming with the Gaussian and EM during before the spring break. We're not gonna have office hours every day of the spring break, but we may have some. So the TAs might announce, we may have, I don't know, Monday and Wednesday or something like this, because it's a spring break. But I definitely gonna assume that after the spring break, there's no more discussions of EM. Okay? So, EM then. Where are we? So what I want to do again is to fit, say, a mixture of a bunch of Gaussians to data. That is, this is my space X of emails or patients or images, whatever I have, and this is the probability of that particular X. So I have an X here. So I'm going to draw it here somewhere. And then there's 3 probabilities of coming from 3 Gaussians. See, my formula here was last time. Probability of X is the sum for K equal 1 over 3K of pi K normal distribution X given K. So each one of these normal distributions is the Gaussian function, and this is a mixture. So my actual function is something, it's gonna look a little bit like this. That's my P of X. It's a linear combination of 3 distributions. I'm gonna need the sum of pi ki to be 1, right? For this to be a valid density function. And what we said is, this is what we want to do is to optimize the log likelihood, right? So what we call for each, so data point is xi, right? We have zik is the membership variable. Zik equal 1 if xi is generated from Gaussian. Okay. By generated, I mean that's the whole underlying story of these generative models, that data comes from three sources. And here's a source that generates patients of a certain kind, a source that generates patients of a different kind, and a different kind. And so when I get a patient, I don't know which one of the sources or problems or whatever happened to them. So it might have come from here or from there or from there. But I'm assuming these underlying generative models, even though in practice, if I'm in a hospital, patients are not really generated by disease generators. There's no such thing, right? Images are not generated by machine. You know, this is just people taking pictures with their cameras, right? But I'm gonna assume that data follows this generative model, that there are three causes of diseases, or three places where people can come from, or three sources of emails, and each one of them has a certain density function to produce data. But if for any data point, this is extremely important to realize, ZIK, it's a random variable, right? I'm never gonna know for sure where that patient came from. This is the main difference between a soft K-means and the real K-means. The real K-means or discrete K-means, I'm gonna iteratively assign a black and white membership variable. I'm gonna say this data point came from this cluster. Now at the next iteration I may change my mind, right, about K-means. I reassign the memberships and I change my mind. That's possible. But at any moment in time, including at the end, it's a black and white variable. This data point came from this cluster 100% and not from the other clusters. In here is the opposite. I'm never gonna know for sure where this patient came from. So it's always a probabilistic. So this ZIK, I know there's a question. ZIK is 1, and I'm gonna see ZIK is the probability of ZIK 1 given example. So I'm gonna say, all the thing I can know about these membership variables is not which one's exactly 1 and which one's at 0, but rather what's the probability from coming from there versus from there versus from there. What's the question?
So, as we discussed before, neural networks are universal approximators, right? So, can we assume that we can represent the same problem, we can solve the same problem that neural networks solve using GDA? Because essentially what GDA is combinations of, linear combination of various Gaussians.
So GDA is something else. There's a confusion here. There is a mixture of Gaussian. There is GDA, Gaussian discriminant analysis, and there is neural networks. So GDA is one Gaussian. It's not a mixture. It's one Gaussian, but it's very multidimensional. That inside matrix can have 50 dimensions or 20 dimensions or 100 dimensions. How many dimensions data has? I'm going to show you some examples on my laptop. Right? This GDA, even though in GDA I'm signing multidimensional Gaussians, multidimensional Gaussians allow me to model the data without making independent assumptions, because that covariance matrix that has 50 dimensions can deal with the relative correlations between the features. But it's still only one hill. It's a hill in 50 dimensions, but it's only one bump. There's one mean, right? And that's it. In here, you can get multiple bumps because I'm summing up few Gaussians.
So can we represent the function to this function?
Right, we can every time we fit a function, it may be possible theoretically to get multiple bumps, but in multi-dimension, this becomes a very funky operation. Like it's hard as it is, the EM, you can try to fit it in many dimensions. There are some things that I didn't say last time about EM. So I give you the formula that makes sense, which I'm going to put on the board right now. But then we're going to see where they're coming from, and that they're not exactly optimizing the likelihood. There is a little bit of tricky business in there. But then the question that he asked is, how about neural networks? Right. So can I map the whole GDA thing into a neural network? I think that's the question.
It's actually, so we can compare neural networks on one hand and mixture of Gaussians on the other hand. So we can represent a function using mixture of Gaussians and the neural networks are universal functions.
So from the point of view of classification purposes, right? I think it's better to think conceptually as a neural network or a regression algorithm or a decision tree, more like a discriminative algorithm. A discriminative algorithm is trying to find the difference between black and white. You like think about neural networks are a pain, so let's ignore that for a moment. Let's think about decision trees. In a decision tree, we very explicitly say, how do you make a difference between a sick patient and a healthy patient? In fact, you tell the decision tree, find me the difference, right? The moment you go to all those splits and all those features and all those thresholds and you try to, maximize information gain or minimize square loss, whatever, you effectively tell the tree, look for all possibilities, all the choices you can make, splits or whatever, and find me the one that differentiates the sick from the healthy. Okay. Email spam versus non-spam. This is the nature of discriminative algorithms. They're not really trying to model the data. They're rather trying to find the separation. Regression is the same thing, right? If you think about forget about regression, perceptron. It's trying to find exactly the line that separates best the pluses with minuses. We're going to see this more pronounced in support vector machines. But it's explicit. Find me the line that separates the best the pluses with the minuses. It doesn't mean that that line models the data. In generative algorithms, we're trying to model the data. So GDA models the plus class separately, the minus class separately. Naive Bayes does the same. It's just a different model. And then having those models, we try to classify the data by using Bayes equation, right? So it's Bayes equation, we want the P of y given x, right? The property of the class given the patient. But instead, we're saying, well, I'm going to use these which I learned from data, right? Because for each class, I learn a probability distribution with my generative model. And then I'm going to weight properly Bayes telling me that I have to reweight this with priors to make it right. But effectively, we're learning the generative models which are here, and then we do classification using Bayes formula. Is that answering the question? Yes.
So do we treat each bounds or each distributions as a cluster?
For each class. So we train one for the positive and one for the negative. And the models are whatever you can fit. You can fit a naive Bayes model, a Gaussian model, a mixture of Gaussian model, a Bernoulli distribution, whatever you think it fits to data. But because we fit it per class, there is really no discriminative notion there. In the plus class, there's only plus examples. In the minus class, there's only minus examples. So when I fit the data to that curve to that data, I don't really have a discriminative notion. I don't try to separate nothing. I just have the plus data, and I'm trying to fit a density function over it. A density function, again, I'm trying to model what data points are more likely and what data points are less likely within the plus class. And there is separately the minus class or the red class or the blue class that says, again, how do you model the frequencies here? What data points are more likely? So if those would be patients, that would be in the class of healthy patients, what is more typical? Typical would be the center, if I have a Gaussian, and then it's going to go down. So I think those questions are very good, because at this point, assuming you guys are just starting data and machine learning, it's much more important to have a fundamental conceptual understanding of this. What is it that we're trying to do here, rather than those formula and the math derivations. Formulas and math derivations, you will have time for it as you go along, depending how much you want to go into the math side of things. But it's essential to understand first where these models come from and what they represent. And then you'll see how much math you want to do.
Just to follow up on the previous question, are they are generative models a different way of thinking about discriminative models, or are they fundamentally different?
So there are mathematical equivalences. You can prove that under certain assumption, regression does the same as a naive Bayes. That's true. But I think we want now to think of discriminative algorithms are the ones that are trying to find separation between pluses and minuses, or red, blue, and green. And generative models are the ones that are fitting those parametric models. Every model has some parameters like means, variances, whatever. And then once I have the models of the data, using Bayes equation, I can ask which class was more likely given a particular patient. I have a model for the sick patient, model for the healthy patient, and I can ask reverse, given a patient, which one is more likely. All right? Good. So now, what's the likelihood here? So I have a z variable. So zik, as I said, they are the memberships. And then I'm going to have this z variable, kind of the whole setup of zik, the whole set of the z parameters. And in here I have the likelihood. Maybe remove the Bayes equation. Of the parameters, right? So I have all those parameters that I'm trying to optimize. That includes in here mu's, sigmas, the covariance matrices, and the pi's. Pi's are the mixture coefficients, and whatever else parameters are in my model. So I'm gonna say this is the log of the product over y equal 1 to n. That's all the data points of p of xi. C parameters. And this is the log of this product. And I'm going to say here that's a product over the components. Probability of xi given So how does this work?
Is this the log I did for one Gaussian or for all of them?
For all of them.
So then, like you.
Because I have from k equal 1 to k, right? But there is a thingy here. This is where we're gonna need an approximation. So remember, generatively, I want to think of every one of these data points coming from one Gaussian. It's just I don't know which one. So that's what this zik comes into play here. The zik, remember, it's 1 or 0, right? So this only going to make that Gaussian that the point is coming from being 1. And the rest of the whatever it's in here not going to matter, right? Because if zik is 0, the only component that matters for each. So this is the over the data points, and this is over the mixture. But in this mixture, there's only one component that matters that has zik equal 1, right? So there's an approximation that we need here. We can't really work with zik because they are discrete variables that we don't control. The only thing we know the probabilities of zik. So even though zik is 1 or 0, In reality, what we have during the EM or during our approximation is not 1 or 0, that's K-means. In here we have probabilities. So what we're gonna need to do is to approximate this with, I'm gonna come back to this point. I'm going to say this in here, VI expectation is the sum from I equal 1 to n, sum from k equal 1 to bk of zik, logarithm of the probability of xi given zik equal 1 plus zik log 5. So from here to here, we have this step of saying, I don't really want to work with zi, which are black and white variable, 1 or 0, random variables. I would rather take the expectation over, when we say with respect to something, that's over all possible values of z, right? When I say take the expectation, I mean I have a random variable, and I kind of average, weighted average, over all possibilities of that z. Now z is not just one variable, z is all the zi's. So the space of z is zi, all the zik's. The space of all possible values of z is all possibilities of distributing these zik's, right? So how would this zik look like? This is I equal x1, x2, up to xn. This is the z's, right? So this could look like, this is from 1, 2, up to k, right? Components. So x1 might come from here, that's a 1, and it has a list of 0, 0, 0, 0, 0, 0, right? This might come from here, 1, 0, 0, 0, 0, 0, 0. Because that's how those membership variables look like. So how many possibilities are here in theory? Every one of those can have the 1 in k positions. So there are k possibilities for x1, k possibilities for x2, k for x3. So this is total possibilities, k to the n possibilities. Right? Hands up who's with me. This is a math detail that is like before. We're going to kind of give you an idea, and it's up to the people who want to go into those details to figure out correctly. It's not required for the class how this works. But it is important to know that in EM, we do this approximation from zik. In K-means, we try to determine zik exact, right? So at the very end, we want to know which zik is 1 and which zik is 0. In here, we take this expectation, work with probabilities. And at all times, we're going to have probabilities. Even at the end, at the very end, I'm not going to have a zik equal 1. I'm going to have a probability of where this point is coming from. So you would have to figure out how the math works when you take expectation. This probability in here, without respect to xi. Remember we talked about this last time? This is the mixture coefficient, which is kind of the size. If you make the analogy with K-means, high pi k's correspond to big clusters of data. Clusters that are more likely for more data points to be part of. This in here is just this in here is square bracket. But this in here is just that normal, right? If somebody tells me zik is 1 for a particular k, meaning the data point comes from the 4th cluster, then I'll use the probability of the 4th cluster, right? So by saying what's the probability of pxi given zik equal 1, that's saying what's the probability of xi if I tell you it comes from the first Gaussian. Then it's just the frequency that the first Gaussian gives, right? If I tell you it comes from the second Gaussian, it will be the probability coming from the second Gaussian is this one in here, right? So this is just the density, this is the normal density function for that Gaussian. So now, we had some formulas before. I want to go a little bit into the math of those formulas, but not the full thing. The math is in the notes. Like before, some people went through the math and figured it out. We put the notes online and we can talk about it, but we don't do the whole math in class.
Professor, so are you saying that you don't have a z vector yet, and then that where you have ones and zeros, those can be basically real numbers? Or
So what I'm saying is in K-means,
Yes.
I'm assuming K-means as a background thing. I'm assuming most of you guys saw K-means already. So
Yes.
I only taught K-means as a recap last
Yes.
time. In K-means we assign ones or zeros,
Yes.
intermediate.
Yes.
And in each round we can change our mind. We can say, no, this data point now belongs to a different cluster.
Right.
So in K-means, this is always black and white.
Right.
One indicates which cluster it belongs to.
Right.
I'm assuming a generative model both in K-means and in here. I'm assuming the data has been generated by 3 sources, and each source has a Gaussian frequency generator.
So we end up with like a matrix of like probabilities for each.
Right, the
set.
difference in here is that this, although I'm assuming this is the underlying truth, I won't know it. I will never know it. So all I know is the probability of this ZI being, this one being the one here. But it could be a one here or here.
Okay.
So I have the ZIK values with the bracket. So ZIK are ones or zero. But because they're random variables, we don't know them. All we know is the distribution. Right? So let me make more clear then if I have this parenthesis here. With ZIK bar, this in this bracket, this is the probability of ZIK equal 1 given Xi. So for a particular patient or email or image, what is the probability of being from 1, 2, 3, 4? Now those numbers are not 0, 1. Right? The ZIK in the brackets, they are real numbers, and the relationship is what? If I sum over all components for a particular I is fixed the data point. If I sum the ZIK, what should I get? 1, right? Because it forms a distribution over all the K possibilities. This is another very good question. It's one of those fundamental blocks of how can I wrap my, what he's asking is, how can I wrap my head around this whole thing, right? And I had a hard time when I first studied EM. I was in a PhD program, right? First year, and I was like, wait a minute, I get the math. If somebody shows me this derivative and this equation, that makes sense to me. But I don't understand the setup in here. So it worth, again, spending some time understanding the setup. What is the difference between ZIK probability and ZIK random variable? Some of you may need to recap random variables a little bit. There's no shame in that. So if you need to do so, please recap them. This is far more important than the math. That's why I kind of skip the math. If you need the math, you will be able to figure it out if you understand the setup, where these quantities are coming from. But not backwards. Even if you get the math, the differentials right now, if you miss the, okay, what was I doing? What are those densities, probabilities, mixtures, so on and so forth? That's the hard part. And that's what you're probably gonna need anyway. Only the people who go to the PhD program is gonna need to take derivatives. Is that makes more light? All right. So let's take some derivatives. Let's see how far we can go with this. The EM basic idea is what? We can't really optimize for everything at once. It's just too complicated, right? So it says don't optimize everything at once. So it says, how about I keep ZI's fixed and recompute, say optimize. Who, if GIK's memberships are fixed, who I can update? Mu's, sigmas, and pi's, right? Because those are the model parameters. And the other one is if I keep mu's, sigmas, and pi fixed, I can optimize or re-optimize GIKs, right? The memberships. That's exactly what Kmeans does. My purpose for recapping Kmeans last time was not to teach Kmeans, was for you to have an analogy between this and Kmeans mechanically. Remember Kmeans? I reassign memberships, that's ZIK. And once I have the memberships, I can recompute the centroids and I can recompute whatever else I need about those clusters. That's a very useful, simple mechanic to have in mind when you talk about EM. Because otherwise, EM could be quite difficult to understand. But keep in mind that K-means. I was just reassigning the points and then recomputing the centroids. That's the same what's happening here. And we call this E step, right? And we call this M step. And we hope by doing this enough times repeatedly, both of them kind of get to the best possible situation. We know that's not always true because you need a certain mathematical property to end up convergent in the right spot. You can get stuck in a local optima. We know that from gradient descent. But nevertheless, that's the hope. So that's the plan here. Now, my plan is to take some derivatives to show you that the formulas that we use for mu's and sigmas and pi's, even though they make sense, they're actually coming from some differential that's set to 0 and so on and so forth. So let's do that at least for mu's. How do I differentiate this log likelihood? Let's just call it LL. That's a typical notation. With respect to mu k. So I'm going to take this formula right here and I'm start differentiating it. I need a formula for this. What is this? What was it? Anybody remembers? 1 over square root 2 pi RT sigma here. Determinant like that. Okay. What else? Exponential of minus 1/2 xi minus mu k. Right? Transpose. That's the sigma k minus 1 xi minus k. The transpose comes either here or here, depending how you set up the data. If you set up as row vectors, they come in one place. If it's column vectors, they come the other way, just to make the product right. You need to have 1d times dd times d1 to make it look. Otherwise, it doesn't work, right? So every time I say this probability, like I said, that's the normal distribution, because in here, zik equal 1 tells me which one is it. Okay, so what is this differential? Let me put it here and let's see where it's coming from. I need to take the differential with respect to mu k of the log of that thing. So here's what I got here, minus 1/2. Is that true? So it's still a differential in front of it. And so what happened here? What happened is I still need I think I differentiated just the inside part, but I still need a sum of Zik times. This is a constant as far as the differential goes, so that distributes over. So where did I get all this? I brought the logs, right? Log of this part, this has nothing to do with the mu's. So log of that is whatever a constant differentiating with respect to mu's, that's 0. And log of the exponential is just what's inside the exponential, right? Because log is the inverse of the exponential. So this is a sum of I equal 1 to n Zik xi minus, now the differential is being executed. This is that mechanic that says if you have this x minus mu square, the differential of that would be 2 times x minus mu. Yeah, and then what happened to the minus, this minus here? What happened to the minus?
That goes away because of the minus in front of mu k.
Right. When I take the x minus mu differential, right, that square, the differential of that is what?
Minus 2x minus 2 minus 2 x minus mu.
Like that?
So minus half of that.
And the sigma remains the sigma here. Because that's constant with respect to mu k, right? Okay. So now if I have this, I set it to 0. Assuming the sigma is not 0, I get sum of Zik, the rest of it has to be 0, right? So how does this work? I open the parentheses, right? Sum of Zik xi right? Has to be sum of mu k is a common factor. This is a sum over data points. So it's not the sum. This Zik, sum of Zik is 1 if you sum the rows of probabilities, but not the column, right? So this results in mu k is the sum of I equal 1 to n zik xi divided by sum over I equal 1 to n of zik. Is that the formula we had last time? Is this a weighted average? Effectively, it's saying take all the data points you have and average them with the membership. Like the ones that have a high membership, they contribute more. The ones that have a low membership, they contribute less. And it's a sum up, by the way. This is a weighted average. Weighted by the ZIKs, which are the membership probabilities. Yes.
So I want to ask about this E step. So first question is, do they really assign ZIK values totally randomly?
Wait, hold on. Before you ask, I think I swapped them.
Okay.
Isn't that the M step?
Then I want to ask about M step.
Okay.
So if the question one is, do we really assign ZIK values totally randomly? Question two, if it is so, then how does it make sense to base our new variance p-pi optimization based on total random values?
So again, how do we do it in Kmeans?
You see random centroids.
Right. So we start somewhere, right? We've got to start somewhere. So in the random centroids will be start with some random centroids in K-means correspond to mu's and sigmas and pi's in here, right? So you ask me where to start this optimization, or
No, I'm asking, do we really assign ZIK values totally randomly? If it is
ZIK?
so-
We know we're gonna actually have ZIK equal 1 or 0. We have probabilities.
But in the
here.
beginning, when we start,
We
don't-
still assign probabilities, not the actual black and
Huh,
white.
but is it random?
So we can start with random probabilities. That is to say, here's xi, right?
It's random, total random would be assigned probability values, right? Is it
for a
really
second.
so?
So if I start, what's gonna happen? She's asking a technical question. If I start with ZIKs equally likely in every cluster, that's not how K-mean starts, right? K-mean starts with which step? Which assignment is made first? I start with random centroids, but then I assign the memberships, right, in here. Right, in here, let's say we start with ZIK probabilities uniform. If I do that, am I gonna end up with 3 Gaussians that look the same? If I say I have 3 Gaussians and my data, I'm assigning every X point that I have, it's equally likely to come from there or there or there. When I'm doing this, I fix a K equal 3 to have 3 components. When am I gonna get the same 3 things? I think I'm gonna get the same. Think about the means, for example. These means, how is this mu1 gonna be different than mu2? The only difference is the weights. If the weights are uniform, the mu's are gonna be the same. So while I think that's possible in theory, I don't think that's a good way to start, to assume I have 3 Gaussians and they're all the same Gaussian. I think it would be better if I start with random centroids, like in K-means. I start with some 3 Gaussians. I say, here's a mu1, right? This is the center here. Here's another center, and here's another center, and some variances. When I compute, that's a E step first. Now I'm computing the memberships, which is probabilistic in this case. It's not like in K-means, black and white. Would I get uniform memberships? No. Because now I have 3 Gaussians, whichever point happens to be here will get a high membership in this Gaussian and a low membership in that Gaussian. But if a data point is here, we'll have a high membership here, low membership there. But then I can adjust the centroids like in K-means and the variances, and I can recompute the memberships. Now, how can I come up with good centroids? Say, ignore the variance from now. How should I get some reasonably good means to start with? What would you do if I give you a bunch of patients or students and say, where would you start with the means?
The mean of
Mean of
those
the
classes. So if I have.
There's no classes here, remember? We have, this is separate for red, blue, and green. So everything is red.
So the ones that are red, the means of those for that Gaussian.
We don't have a Gaussian yet, right? We have just the data, and we only look at the plus class. So everything is a plus. How do I come up with some reasonably good centroids that are not all the same, but they're not way off? Like if I have a centroid here, there's no data here. It's a waste of time.
Means of individual features.
If I tell you come up with one centroid, not 3 Gaussians, just one, how would you get it? Average all the points, right? So in here, what's the meaning of 3 centroids? It tells you there are not one typical patient, one typical case. This is a lot of patients here. They tell you there are 3 different kinds of patients, and there's a lot of patients here, a lot of patients here, a lot of patients here. So what can we do empirically? I'm making a parenthesis now, to get to some reasonably 3 centroids. I'm assuming I know it's 3. That's a problem in both Kmeans and Gaussian mixture, knowing it's 3 or 5 or 7. How many hills do you want? Again, what can I do empirically to get some reasonable approximates of centroids?
Set 1 to the mean of the whole, of all the data, 1 to the mean of the bottom half, the upper half.
Although bottom and upper, he's getting closer, warmer, so to speak. But what's bottom? You mean bottom is this direction,
Yeah,
and upper is
the
that
lower and the
direction.
higher.
The problem is, this is 50-dimensional data, right? There is no
Right.
bottom and up, because it's 50 dimensions to go in which way. If it be unidimensional, you'd say, okay, take my data, right? That's what he means. Take my data, it's unidimensional, so those are real values. I'm gonna split the data maybe in 3 categories, right? And say, 1/3 of the data, that's the bottom, assign a centroid there. Like average those data points, get a centroid. So if this is really unidimensional, I can say, take 1/3 of my data, put it here, the bottom, take 1/3 of my data, create the middle, and 1/3 of my data, create the top. But if it's 2-dimensional, or 3-dimensional, or 6-dimensional, even if I chop each feature in 3 spots, I get a bunch of cells that's exponential. What else can I do?
Calculating standard deviation and maybe
Of the whole thing.
yes, and use this distance as to put other means or other points like evenly same distance.
Right. So I think it's quite a useful thing to think about without me providing an answer. Maybe I don't even have an answer now that I think about it. Right? Think about this way, 2D. No, I have an answer, just I don't want to give it out today. Somebody gives a bunch of data points. There's no classes here. Right? I have a bunch of data points. Again, there's no pluses and minuses, it's just all one set. How do I come up with some reasonably good centroids? Ideally, I want one in here, one in here, one in here, right? That's ideal. But maybe I don't guess them. What I want to avoid is having 3 centroids way out of place or too close together. I have 3 centroids that's actually the same centroid. I want some starting point that's reasonable. So this, yes, you have an answer for this?
Or just use Kmeans.
Right, that's one way to think about it. How about I do Kmeans, which is the discrete version first? It gives me some centroids of the data, and then I play with those centroids probabilistically. Right. This is actually quite a important problem in practice. If somebody hands you a bunch of data, not for the purpose of EM, but for the purpose of trying to see how data looks like, it would be very useful to have your hands on some centroids. To say, I know how this data looks like conceptually. There's a bunch of points that are centered around that value. That's called a typical value. There's a bunch of points centered around this value, and a bunch of points centered around this value. Now, some of them may be more tied together, meaning low variance, and some of them may be spread around large variance. But nevertheless, knowing that my data set contains 3 or 5 typical points, and everything else is a rather anomaly, that's a useful thing to know. So coming up with some sort of clustering idea, K-means, or some other clustering, might be a way to go. There's other clustering that go by similarity and say, let's make, instead of running K-means, we could say, I pick this point as a centroid at random. But then I look at distances from this point to every other point, and I compute how many points are close to this guy. And then I form a cluster there. Every time I have a reasonable cluster or an approximation, I can average that cluster gets a centroid. That's what K-means does. I don't know if this answers your original questions. How do I start this process? I think that the key is to set some mu's first. In my experience with clustering, which is not as big as I have with, say, regression or boosting, but I've run quite a few clustering algorithms. The key for a successful start is not the memberships initially, it's the centroids. It's easy to fix the variances and the pies, the mixture coefficients. What's hard if you start with centroids that are way off. So some analysis of the data or some empirical heuristic, sometimes it's domain knowledge. A doctor or a lawyer or a carpenter or somebody who manages server might know what is the typical email, what is the typical patient, what is the typical book. So then you may have some domain information about how to set those centroids.
When you say hard, is it hard to compute or hard to converge or?
No, I'm saying it's becoming difficult if you start in the wrong spot. So having the initial centroids or mu's analogy from Kmeans right, it's the right important step forward.
If there's a problem at starting with wrong mu's, so the same problem is there in Kmeans also, right? If we start with wrong points. So how would doing Kmeans before to find the centroids help us in this scenario?
Yeah, we're not solving that problem. So I think we can, typically the easiest answer for that is to start with multiple centroids. Start Kmeans not one time, but several times with different centroids and see what you get each time. At least that's a reduction from a probabilistic version to a discrete version. What he's asking is, in K-means, how do I start the centroids? Where do I put them? One of the best approximations I've seen is to start with centroids being sum of the points. And there's an algorithm taken from graph theory called furthest far traversal that says if this is a centroid right here, the next centroid should be far from this one. So pick the next centroid here. And the next centroid should be far from those two. I'm going to get this point. That way, even though those are not centroids, because farther will put, conceptually speaking, the centroids at the extreme of the data set. At least they are far away in different dimensions. So when we do K-means that says what points are close to this, there is a hope for a globular shape, right? K-means works if the points assigned to a cluster are having a convex closure around there, and then in here those points so that's just an idea. I don't want to go now into farthest far traversal, but if you really want something that's not random, that may have some hope with the data, going farther away a little bit to capture the data shape, it's a good idea. The danger with that is that if I have an outlier here, I'm going to set that as a centroid, and that's not a good thing. Not an easy problem to solve. But it's becoming a different topic for right now. Okay? Back to my main story here. Are we believing this answer? It's a weighted average of the points, with the weights being the membership values. How about the other one, the sigma? That's the one that we're meaning some matrix derivatives again. So I want to differentiate that likelihood with respect to the sigma at -1. So the differential of the same thing, log of 1 over 2 pi at the sigma differential of 1/2 xi minus k, sigma k minus 1, xi minus k. This is so what happened here? Not much, right? I just broke this, I think broke the log into parts. And now I get 1/2 sigma k. This is backwards now. The transpose happening. So again, we're using the mechanic from one-dimensional. We're not going to go to matrix differentials again, unless you guys want to at office hours. The log of this, when I differentiate with respect to argument, at least in principle, becomes 1 over the argument, 1 over sigma minus 1. Let's just pretend the sigma k, right? A mechanic is there. The differential of the log is 1 by x, right? And then in here, it just differential with respect to this guy. That's easy. It's this times something, so it leaves that something. If there's a formula with the transpose, that the transpose is moved around in here. It's not this transpose times that is the other way. So there is a formula of matrix differentials that tells you how to move the transpose. Right? If that's 0, we want to. Then it means, again, I missed that sum. There was a sum here for I equal 1 to n of zik. So then who is the sigma k we want? That's the formula we had last time. It's a weighted average of the scattered matrix. That's the empirical covariance matrix, right? And then we weight each data point with a membership to that class. Right? It's a weighted. Now, there is another thing that's going on that's extra in here with those pipes. So how the pipes work out. I would like to keep this formula here. So what about the pipes? For this, we need something called constraint optimization. We need the differential of log likelihood with respect to pi equals 0. We want, just like before, we want 0. But there's a constraint. What's the constraint? The sum of pi k has to be 1. So constraint optimization, a very popular way of solving those is with Lagrangian multipliers. I will leave it at that for now because the formula that we already gave last time is much more intuitive than the math. If we have time this term, I'll go over the Lagrangian multipliers because there's some machine learning algorithms that actually need it. In here, you can just go by the size of the cluster. So we're gonna get people math oriented, we can figure out where these formulas are coming from. So Lagrangian multiplier is this lambda. Because the sum of the pi k is 1 here, that implies lambda. So who's pi k here? Sum so sum over all the data points divided by lambda. But because the sum of pi k is 1, that means lambda has to be the sum for I, sum of k, zik, that's got to be n. So that means pi k has to be sum of zik. The way Lagrangian multipliers go, you introduce this Lagrangian value. It has a geometrical, very intuitive explanation of how the constraint has to play out with the things that we want to optimize. And therefore, we're obtaining an equation something like this. That's the actual equation coming off here. That means we can compute pi k as a function of lambda, but then we use the constraint to compute lambda. And the result is something very intuitive. We already seen it last time. This is the proportion of members in cluster K divided by the total, right? So analogy with Kmeans, if ZIKs are 1 or 0, this will be how many points are in cluster K divided by the total. Will be the proportion in that cluster. That's why I said the easiest way to think of this mixture coefficients is how many data points are coming from each side. If you have data, say, from 3 hospitals, you put all the patients together. And each hospital you model with the Gaussian, there will be how many points here, how many points here, how many points here. If one hospital is dominant, it has the vast majority of patients, then that pi k become close to 1 and the other to 0, and then the whole mixture become looking like the Gaussian from that hospital that has a higher spike. Good. Now what I want to do is to go back a little bit into this.
Professor, so when do you stop? What is the, like, are you going to convergence, or are you just
Right.
gonna
All these algorithms
Right.
have to have a stopping criteria,
Right.
and there are complicated ways to look at this. But the simplest way, which we don't have to go beyond that in this class, is to say when things are rather stable, right? When things are not changing that much. So for us, what does that mean? Not changing that much. ZIK remain roughly the same like before, the probabilities don't change, which is the same like in Kmeans, right? If points roughly get assigned to the same cluster as before, all of them, then the centroids will be the same, and then nothing changes. So as I have to have a way to measure this mathematically, I'm saying it in words, but what does it really mean, things not to change? How do you measure between the old ZIK and the new ZIK, whether there's a difference? That's what it comes down to. There are functions that will take ZIK as a distribution per data point and measure the old distribution versus the new distribution, something like the KL distance, for example. I can also use the square error, but that's not really appropriate for distributions. I perhaps can measure that difference on the mu's and sigmas. If I get the same mu's and the same sigmas, that probably means I'm, again, in a stable situation. Stability is not a problem usually to measure when things get stuck. EM gets stuck. If you'd like an anecdotal answer, it gets stuck too quickly. Like, we would like EM. What happens when you're going to run EM? You're going to run for a few iterations, and you say, okay, it got stuck, meaning nothing moves anymore. But you know you don't have the right answer, right? So on all these optimizations, the problem is not that we don't know when it's stuck or when the values don't change. The problem is that it happens too early because it got stuck into an optima that's not the optima that we want. So sometimes if it happens too quickly, you may want to restart the start with a different initialization just to run it again.
I just want to know why you're differentiating with respect to sigma inverse and not sigma. Will it make a difference?
So I don't think that matters for the purposes of setting the differential to 0, right? I think it's just easier the math.
So it's fine if you update the sigma values with the differentials you get from sigma.
So isn't it the case that if I differential with respect to sigma is 0, the differential with respect to sigma inverse is also 0? So that, I think that's the purpose, is to take it here, the differential of sigma inverse, because the math works easier that way. I don't have to, if I take the differential with respect to sigma, I'll have another matrix operation that the sigma minus 1 differentiate with respect to sigma. Perhaps that would have been the answer to the other problem that we had. That we can differentiate with respect to sigma minus 1 and get it easier that way.
Just to make sure that I understand correctly, so in classification problems, ZIK probability values is going to come from training data sets, right?
No. If we would have, so that's an excellent point that we need everybody to understand. I have the E step and the M step. The E step is computing ZIK given the parameters.
Even in classification, you need to have this.
Right. Every time I fit this to data, so in classification is just fitting to 3 classes. That's what it is. If I have either one of them, you have the parameters and I want to compute the ZIK, that's extremely easy. If I have the ZIK and I want to compute the parameters, that's also extremely easy. The whole point of EM is that it's a chicken and egg problem. I don't have the ZIKs, therefore I don't compute the parameters in one shot. And I don't have the parameters exact, because I would be able to compute the ZIKs in one shot. So I have to go back and forth between the chicken and an egg to see where it's optimal. There's an overall loss that I can compute here, just like in Kmeans, right? To see when is that going down, the likelihood loss. But I can't assume I have one of them. So this, it's computing iteratively the parameters, the memberships, parameters, memberships, until at the very end when we say, okay, I think we're done, we have both the parameters and the memberships. So they don't come from data. We have to calculate those.
So it's similar to clustering problem. It's similar to finding
Right,
correct means
One
of
easy
the-
way to think about all this is K-means, except the memberships are not black and white. So in K-means we do the same, right? We compute the memberships, then we recompute the centroids that are the parameters, so on and so forth. And here we do that, except the memberships are probabilistic, and the models are better defined. The models don't just have centroids. They have the shape, the variance, right? And they also have the mixture parameter. In K-means, do I have a mixture parameter? Is there an analogy for this pi k in K-means? I mean, I just said it 10 minutes ago. What's the analogy in K-means of this pi k?
You do the weighted average using the number of points in each cluster.
The weighted average, so in K-means, the weights are 1 or 0. Because a point, it's either in that cluster or not. If I take the average, I get the centroids. Right? I take the points in one cluster, average them, that's the centroid. But what's the analogy of pi k? The analogy of the centroid is the mu k. What's the analogy of pi k in K-means?
Size of
The size. How many points are in that cluster? Look at this formula. This is all 1 and 0 memberships. What is this? It's the number of points in divided by the total. So there's no explicit pi k in K-means. It's just how big the cluster is. Okay. What's going on? This is a small parenthesis for the math-oriented people, an exercise. What's actually going on with this expectation? So when I said here, we don't want to work with CIK, that's way too difficult. The space of that is a k to the n exponential space. Imagine if this n is 100,000 data points. There's no way to deal with this space in a discrete sense, right? So we're taking expectation with respect to the zi's. But then, that's okay, we're taking expectation. We are actually maximizing a different function than the likelihood. The likelihood is that one. And we're saying take the expectation with zi. You can call this an expected likelihood, if you like. And that's the one we maximize. This whole EM is the formulas, everything is derived to maximize this, which is not exactly the likelihood, so to speak. It's an expectation. So why does that work? Or how does it work? Let me see here. Log of probability of x given parameters. This is the expected value of the log. Let me write it next. This is the log of probability of x and b given the parameters. The notes have a general theta for the parameters. I would like to write the params so it's clear for you. Parameters means mu's and sigmas and pi's and all that. Not it was not notation. So what it's saying here, the expectation is taking all the possible values of zik, that's the membership variables, for some distribution of zik, which I don't know. I don't know how the ziks are distributed. That's asking a question about the data, right? today I may have so many patients from here, from there, but if I wait 6 more months, I may have different patients from that hospital and that hospital and that hospital. So overall, there's a grand probability distribution of memberships, and that's we're gonna call in a note, this is Q of Z. Z distribution. That's the distribution of ZIKs over all the possibilities of where the points might come from, these ones and zeros. Question?
So once we have fixed our parameters, when do we update it? For example, if new patient walks in, then when do we update our model?
So that's a domain knowledge problem. You know, in practice, there are concerns about computation, like how hard it is to update the model. There are concerns about productivity. If I update the model, it's how long people have to wait. Sometimes I take a Sunday or something to update the model so that people can use it next time. And then there is a concerns about the data. The problems I know in industry, medical data, they say it's totally fine to wait for 6 months to update the models, unless something is changing. Sometimes in medicine, they change the classification of codes, for example, the billing codes. And then you gotta know when that happened and be very careful how you update, given that there is a data shift. So you don't wanna combine necessarily the old data with the new data. But you have to have some knowledge whether, for example, doesn't work like that, right? Whether you can't wait 6 months to update the weather model. You gotta update it. You know, if you look at the weather updates every 3-4 hours, the models get updated if a storm's come, right? So then, I think you have to have a sense of how much data you get for your sensors, which are patients or weather sensors or whatever, and at what point the new data overwhelms the old data. It's also the case that in weather, the new observations are much more reliable than the old ones, right? Even if I have a lot of data, what I observed today about the temperature and the clouds or whatever, I can discard what I've seen last week. But in radiology, patients is not like this. What I've seen for the last 6 months is probably in line with what I'm going to see in the next week. So I think that's a data decision. At what point do we update? Just a quick parenthesis on that, in industry, the most delicate updates are the ones related with some things have changed. You have to be aware of that change. I mean, here's a strong advice for you. If something has changed in the data you work with for a company, you gotta be on top of the guy who understands the change. Don't make updates until you know exactly what the change is, because that's where most things go bad. You know, when there is some update that you don't know, what you do, you take the new data, you rerun your models or whatever, out of a sudden, nothing works anymore. You gotta know what has changed. Out of a sudden, a company went bankrupt, they can't make payments. And you don't know that. Out of a sudden, a code has changed. Out of a sudden, a doctor is in vacation and a new doctor replacing him does things differently. Out of a sudden, there is a crisis and the bank doesn't give loans anymore. You gotta be aware of that change before you train your models. One more thing, in Wall Street, when there is a crisis, you know how much, most of the trade now is done by machine learning, right? There is no good way to stop it. People just unplug computers from the wall. You know, like because machine learning will go nuts when a crisis happens. Machine learning cannot model a crisis like a 9/11 of that magnitude or something like this, right? There's no enough training data. There's no way for AI to deal with stock market in an event of a terrorist attack. So what people do, they just shut down the servers to not, because if they don't shut down, the machine learning would buy and sell stocks, right, by itself, and that's not good. So again, this is an extreme example, of course, but all kinds of things like that crash, you know, self-driving car. Once something go way off the training model, right, there's a crash already. The machine must have a much more simple rule heuristic how to stop, you know. In fact, that's the rule that's implemented. Something off the model, just stop the car. Don't turn off the AI, just put the brakes, done. So, you have a question?
Yeah, I was going to say, if someone updates like you said, the codes where you're trying to classify, don't you have to throw out all of the old data?
No. most of the old data is still useful. What happens is typically people retrain or do an update of training if algorithms allow that, using all the data that's available. So it doesn't mean like if I have new patients in the last 2 weeks, I'm gonna throw all the patients from.
Not for new data, when you said when there's a change in what the data is, like for example, if they update the medical billing codes, then all of your old data will be predicting the old billing codes, right?
Well, what people do, that's a good question. You know, if there's a data shift, can I still use the old data? So people have tried to manually map the old data into new data to say, okay, for every old code, what's the equivalent new code? That may be more problems than solutions there. Like you may introduce other problems. Other people have tried to map everything into universal concepts. They say, here's the new codes, old codes, and they all map to this particular concept, and they predict the concepts. And then if I want old data, I translate back the concepts to old data. If I want new data, I translate back the concepts to new data. A lot of the NLP works that way. Try to predict some concepts that are related to certain words in certain languages. And there's once I have a data model by those, what's called in graphs factor nodes, then I can map those factor nodes back into the raw data that I have. That's a good question. Should I throw the old data when there's a data shift? Well, depends if I can make use of it. In the billing codes, they managed to make use of it. They map an old billing code to the new ones. It's actually one-to-many mapping. So every data that has a new code becomes probabilistic in the new codes, because it might be that one or that one or that one. They try to use it. The data has been, the US government should make this shift in 2015. That was a problem right then for a few months because there was not enough new data. Once I've collected 2 years of new data, I don't need the old one, right? Because I have enough new radiology and X-ray or whatever it is that I'm predicting. But it's a problem right away. I don't have new data, so I'm blind at guessing. All right? So I'm trying to do some math here, right? But you guys don't like math that much. So this is log of, well, it should be a sum, right, over all possible values of z. Z values of probability of x, z given params, right, times so where to start and when to end this thing? Make some changes here. So what I want is to have here log of sum using. Oh, hold on a second, don't take notes yet. The problem is with Q is hard to manipulate and I don't know it, but I think the expected likelihood comes later. So what is it saying here? Logarithm of this probability, right, depends on who is the z-value for that point, right? So whatever values I see in data is going to dictate what likelihood functions I'm going to use, right? Which Gaussian is the one I'm going to use. That, I don't know the z-values in data, so I'm going to replace them with this unknown Q function, and I'm also going to replace the sum to be exact with an integral, because the z's are continuous in terms of the probabilities values they have, right? I'm not gonna model zik as discrete values. So then I'm gonna get when you put an integral, you need this dz here. So that's the integral over z. Now, there is an essential fact here that says that this is bigger than do you remember that inequality about logs? The log has a certain property, right? This is the log function. And we did this before. We were saying if you take the average of 2 points, x1 and x2, this in here is who? Is the log of x1 plus log of x2 by 2. And this in here is who? Log of x1 plus x2 by 2. So that's a property of log functions. That's why if you have, I missed a log in here. This log of a weighted sum is bigger than the weighted of the logs, right? So this is log of weighted sum. This is the sum of weighted logs, right? So because of this is true, it will allow me to, now the log in this one breaks in here, right? The log of a fraction is the difference in the logs. So I'm going to get something like integral of qz log of p minus the integral of qz log of q, right? Because the fraction breaks into a difference of logs. Point is, this is the expected likelihood if Q is the true distribution of Z. This is the stuff that we are maximizing, not the actual log. So if somehow we drop this term off, which it's not a matter of parameters. Whatever the distribution is, it's going to be a constant, so it doesn't bother us. But what we did was an approximation, right? So how does the stuff look conceptually? This is the log likelihood, and this is what we actually maximize. This is the expected of log likelihood. This curve, it's a much nicer curve, is the one we're maximizing. And this theorem here says the log that you want, it's bigger than this, because this is a positive quantity. So we're not really maximizing the log when we update all parameters. We're updating this expected value, which, like the theorem says, this is a lower bound. So it's always below the actual thing. So is it true that when we maximize this, did we actually maximize the actual log2 guaranteed? No. So why don't we maximize the log? Because we don't know how, it's too high, right? But we know that the expected log is a lower bound of it, and we're pushing that function up with the m. Now, I don't need you guys to know the math of that, okay? How this came up. Like how does exactly the Q function works and nothing like that. What I need you to know is this inequality about logs. When I see logs, especially log of a sum, it's a very difficult mathematical object when you have log of a sum. It's hard to work with that because the log of a product is nice, but log of a sum is very difficult. So instead, we create an approximation. We say, you can maximize that, or we don't know how, so we're going to maximize this function that's below it. So when we push that up, it's possible that the log has another maximum in here like that, and then we found this maximum. The corresponding maximum of the log likelihood is not this one, it's this one, so we missed that one. That's possible. But in principle, it's pretty good enough to maximize this expected log likelihood. Now, the Q is going to work fine from data. We don't know Q, but if we play with enough data, the data will be a simulation of what the true Q is. So, just to recap this part, you need to know this inequality about logs, and you need to know that EM is actually maximizing the expected likelihood. It's not the true likelihood.
When you say the expected value of the log likelihood is this lower bound, that doesn't make sense to me because the lower bound is always going to be less than the log likelihood.
Yeah.
Right? It's just that you expect that they're both maximized at the same place, right? You don't expect that they're always the same.
Yeah, this is the empirical expectation. Is what I get from data. I don't know Q. So this inequality works for any Q, just because this is a positive side. And the Q I'm relying on is the one that essentially is given to me by the data. There is a term here, which is the entropy of the Q, effectively. And that gets dropped from the optimization. I'll have to think a little bit to give you a more detailed answer of that question. I think your question is the expected can be lower than the likelihood because it's an average, right? But in this case, I think we have to look exactly how this Q of Z plays out in here. Because I don't think we have the actual Q, we have just what's estimated from data. I was planning here to show you guys some things on the computer. Let me see if I can do this quick. And we'll have to do this, continue this next time. I'm going to show you the basic stuff right now, and we'll have to do some, show you some other stuff. How do we, it's a nice Gaussian, right? I want to insist on this again for people who have not seen a lot of statistics. How does these two-dimensional Gaussians work, right? So here's a Gaussian. I don't know if you can see my Gaussian matrix here is 0.25, 0.3, 0.3, 0.1. This one looks, that's the, remember when I told you look at the Gaussian from the top, you only see the footprint on the axis, that's what I mean. And if you see, look at it from the side, You see how it's skewed one way and wide the other way, and how it's not aligned to the axis. It's not aligned to the axis because it has covariance, right? In this matrix, if I put the 0 for the covariance, I get it aligned with the axis now, right? And it's wide one way because it has a variance of 1 on one dimension and a 1/4 on the other dimension. So 1/4 make it skinny on the direction that's 0.25 and wide on the direction that's 1. Okay. So that's the basic covariance matrix that gets sigma in the Gaussian. And you gotta understand how this works first. Because all these Gaussian mixtures and GDA and all that requires this Gaussian multidimensional function in it. The other stuff I wanted to show you here is if I run, you're gonna have an exercise. We are not connected to internet. Let's begin with that. You're gonna have an exercise here that asks you for running EM for a basic stuff. These two Gaussians, it's a data generated from a Gaussian. So we have the means and variances, so you're gonna know exactly when you got the right answer back, because the data is generated from this model, which is not the reality. In reality, the data is not generated from So in here, when you run this and if you plot it after every iteration, that's what I have here. I'm going to show you the plots directly. What happens, it will be, this is a pedagogical exercise. Of course, data generated from two Gaussian distributions with 2 dimensions, or you have another one with 3 Gaussians in 2 dimensions. Don't confuse the number of dimensions, dimensionality, that's the sigma, the D, with how many Gaussians you have. You can have 2-dimensional data, like in here. This is 2 Gaussian because there's 2 groups of data. The red dots come from one Gaussian and the green dots from another Gaussian. But I can have data coming from 3 Gaussians, also 2-dimensional, red, green, and yellow, or, you know. When you plot it, you're gonna see how your EM program works out, right? You will see that the EM is trying to balance those Gaussians. Of course, we're gonna cheat, we're gonna know K. We know it's from 2 Gaussians, so we're gonna set K equal 2. Otherwise, you'll have to play with this K. And then you'll see that at the time of convergence, you should be able to replicate the input parameters, the actually mu's and sigma that were used to generate the data. And you'll also see that the sizes, those pi k's, are actually matching the sizes of how many green points and how many red points you have. So when you get there, you know you got the right answer. But I think you should look intermediately of, okay, is my updating pi's, mu's, and sigma going in the right direction here? Is, I'm getting closer to what the data is like. Finally, we have this homework due soon. So some things here are grad only. One of the grad only problem is not Gaussian distributions. It's still a mixture, but this is not on Gaussian distributions. I'll have to talk a little bit about that on Thursday. You have the update formulas, so these update formulas are just a little bit different than the Gaussian distributions. Those are Bernoulli distributions. So I can do the math for people who want to do the math with Bernoulli distributions. Also, when you flip coins, you don't get the Gaussian distribution, you get the Bernoulli distribution. It's not hard to differentiate it, it's all the same like before, but you don't need the differentials to implement this thing, because you're going to write an algorithm and you just need different updates in here to run the EM on coins. And I think This is where I'm gonna stop. I'll have a demo on Thursday on all the info. I don't think, my recollection of that moment is that you probably still have enough data. I don't think we play that. Whether you make it one or many.
Yeah, that's the idea. No, that is
These deadlines are not exact. Get it done. And then you can get them you mean right now? Yeah, we can sit in private. We don't have to go all the way to the office. We can sit after the Let me come. As long as you know how to do the E&M step. The E step is the same. The Z memberships gets computed the same way. The M step that updates the model